board? Excellent. All right. So for this part of class, you're probably going to want like your notebook, wherever it is you normally take notes, because I'm going to show you how to solve conservation of energy problems, right? And to start off, we've talked about energy conservation quite a bit over the course of the past 2 days. And when we talked about energy conservation, we talked about it in terms of the total energy staying the same. So, by definition, energy conservation says the total amount of energy in a closed system is conserved. And I just put little pointers on what that means. Closed means that the objects only interact with each other. So, let's say I have like the ball earth system. I would assume if they only interact with each other, that there's no friction and there's no air resistance. Okay, so closed system, they only interact with each other. Conserved means that the total amount of energy stays the same at all points. So if I have a point A and a point B, maybe they have different kinetic and gravitational potential energies than each other, but the total is the same. And when we say total, do you remember like the 8 forms of energy? Total is add all of those up. So total includes, yes, your kinetic and your gravitational potential, but total also includes heat and light and sound and chemical and you know the rest. There's a lot. So these were the be like the word definitions. And what you'd probably see on a test is something along the lines of a multiple choice. Like, where is the energy greater? At A, at B, or at C? And it would be a trick question because the total energy would be the same anywhere in the closed system at any point in time. So that's the word half. Let's get to everyone's favorite, the math half. So here's what a conservation of energy problem might look like. So in this problem, I've got a cannonball shot horizontally at 30 meters per second, and it starts at 20 meters off the ground. We want to calculate how fast is the ball traveling just before it hits the ground. This is a conservation of energy problem. So I'm going to start off by doing all the stuff we did in class yesterday. So let us name the system, identify the reference line. Reference line we're going to draw at the ground. My system is going to be the ball earth system. If you include the cannon, it's pretty much irrelevant. You can include the cannon or not, and it doesn't change the problem. Because at point A, it is already outside of the cannon. Right? So we got our reference line, our system, and then we identify the energies. At point A, there's both kinetic energy and gravitational potential energy because it is moving and above the ground. At point B, we're going to make this nice little assumption here. It says just before it hits the ground. So I can assume at B that it's functionally got zero potential and that all of it is kinetic. Right? That's going to be an assumption we make a lot just because it makes the math easy. It means that all the energy in point A is now kinetic energy at point B. So the reason we were spending so much time on energy systems and bar graphs is so that we could get to this one equation quickly and easily. So in picture A, the kinetic plus potential turns into kinetic energy at picture B. Let us use this to solve a problem. This is the new stuff. All right, so I've identified my system. That's step one. Step two, calculate the total mechanical energy in the system. Now, at A, the total mechanical energy is kinetic plus potential. And at B, it's all mechanic or all kinetic. There we go. And I don't have enough to solve for B yet. Since I don't know the speed at point B, I can't calculate it yet. But I can totally get the total mechanical energy at A. At A, I know the mass and the velocity and the height. I can do that. So step two, calculate the total mechanical energy. The total mechanical energy stays the same no matter what point it is in the system. So if I can find it at A, I know it at B too. At A, it's going 30 meters per second and it's 20 meters above the ground. And this means there's 2,250 joules of kinetic energy and 980 joules of potential energy. To find the total, I'm just going to add them. So in this case, the total mechanical energy, it's 2,250 plus 980 gives me 3,230 joules of kinetic energy. So if step 1 was identify the system, step 2, calculate the total mechanical energy. Step 3, set the total mechanical energy at A equals the total mechanical energy at B. That means I know exactly how much kinetic energy is at B. And if I know how much kinetic energy is at B, I can solve backward for velocity. Substituting in 5 for the mass, dividing by 2.5 on both sides. My last step is to either solve for a missing speed or a missing height. So I divide by 2.5 on both sides. Square root is my last step for 36 meters per second. So to recap, here's the steps to solve a conservation of energy problem. Step 1 is actually this whole, like all the stuff we did yesterday. So draw your reference line, identify the objects in the system, identify the energy at each point so you can write an equation for total mechanical energy. Then calculate it. Calculate the total mechanical energy. You're either going to know it at A or at B, and you just set them equal to each other. In this case, the total mechanical energy, well, we didn't have anything for spring because it wasn't touching a spring. So sometimes one or two of these terms will be 0. Spring was 0 at A. And maybe a thing to add here would be to calculate the total mechanical energy at one of the points. Right? Because if we know it at one of the points, then we know it at both of the points. In this case, I started with, 3,230 joules. So I end with 3,230 joules. And once I set the before equals after, solve for the missing height or velocity. So let us show you another one. I'll show you a thing that might trick you up, and then we'll be good to go. So let us show you another one where it might have something that kind of deviates from these steps. Let's say instead of a cannon, I've got a roller coaster. Well, that looks fun. All right, so in my roller coaster, I've got a 50-kilogram person, and they sit stationary at point A. This is the person-Earth system. The Earth gives the person their gravitational potential energy. And at A, they're stationary, so no kinetic, just potential at A, and no spring. It's not a spring-launched roller coaster. At B, it is both above the ground and moving. Fun fact, if it is not moving, if it's not moving at B, the person, they don't have enough momentum to stay on the track. They'll fall straight down. They will just projectile straight down into the upside down into the roller coaster track, and that would be unfortunate. So they are moving at point B, which gives my equation the potential energy at A is equal to the sum of the kinetic energy plus potential energy at B. That's step 1. 2, calculate the total mechanical energy. At A, we know the total mechanical energy because we know the height. So I'm not going to try and calculate it at B because I don't know the speed at B. I can't calculate the total mechanical energy at B. So let's do it for A. At A, there's only potential. So MGH that. And that gets me 14,700 joules. And here's the thing I was saying that might throw you off. I have 14,700 joules of potential, and that's going to split up into a combo kinetic plus potential. But if I don't know one of those numbers. Let's say I don't know either the kinetic or potential. I don't really know what ratio these two are at. All right. I don't know which one is going to be greater than the other. Like I drew one because I know the answer at the end. You might, as a sub step, need to calculate PEG so that you can get the kinetic energy. If you can figure out the potential energy at B from its height, then we can solve for the kinetic energy. So sometimes if you're missing an energy, there is enough information elsewhere in the problem to find it. Okay, so at B, gravitational potential energy is like 9,800 joules. I took the mass times 20 meters in the 9.8 gravitational field, and I could use that to solve backward for kinetic. Okay, but once I know the kinetic energy, I can move on. Because step 3, set the total energy before equal to the total energy after. Step 4, use that to solve for the missing velocity or speed. So subtracted 9,800 to the left, substituted in 50 for mass, divide by 25 on both sides. Square root is the last step to get my final speed. So when I solve a problem like this, the key is that I'm taking the energy in picture A and setting it to the energy in picture B. The total mechanical energy is conserved. The one other way you could use this is for height. So let me show you that last way and maybe a shortcut. I feel like you guys would probably appreciate a shortcut. A thing you'll have noticed though, this is not math you should be doing in your head, friends. This is not math that like I could sit there in my head and like take the square root of 196. I'm not going to do that. And you shouldn't do that either. So we're going to do the same steps. You should do these steps with a calculator just because it's going to help you like keep track of the numbers. It'll also, if you get a graphing calculator or use Desmos, it'll also help you keep track of order of operations. That is a drawback from the ones that are built in the phone. They don't do a good job at order of operations. So let's say I have my last example. Rocket problem. Let's solve for a missing height this time. So I've got a 15 kilogram rocket launched at 60 meters per second from a height of 12 meters above the ground. This is not drawn to scale at all. Calculate the maximum height. So my reference line is going to be the ground. It starts at 12 meters. How high does it go? It's going to be the rocket Earth system. At A, it is moving at 60 meters per second and it's 12 meters above the ground. But at B, it is stopped. So 0 kinetic, all gravitational potential. And for all of the problems that you and I are working on mathematically, we're making this assumption that there's no loss to heat. So this EINT is going to be 0 because we're assuming there's no air resistance or friction, no loss to heat. So my equation looks like kinetic plus potential equals potential. So let us substitute and solve some things. So I've got my system identified. I've got my equation. Let's find the total mechanical energy. Since I don't know the height at B, I can't solve the right half of the equation. Let's solve the left half of the equation. The total mechanical energy is going to be the sum of the kinetic and potential at A. So I'm putting in 15 for the mass, 60 for the speed, 12 for the height. And that means I have quite a bit of kinetic energy and not a huge amount of potential energy. At point B, all 28,764 joules are going to turn into potential energy. So mathematically, if I start subbing some numbers in, I've got 27,000 kinetic plus 1,764 potential means that there are 28,764 joules of gravitational potential energy at B. So then solve for height. If I know the amount of energy, substitute in m and g, solve for h. So I said there was a shortcut. There is a shortcut here, but I want to point out that it only works with the systems we're working on right now. When I add springs in on Tuesday, forget I said this. All right. There is a shortcut if you're working on problems in a little bit and you're like, I would like this to go faster. And the shortcut is you can actually figure out the height without calculating the total mechanical energy as a substep. How that works is, let's say I put in 1/2 mv squared for Ke, mgh for Peg, I can see that the masses cancel. And probably a good note to put to yourself is that that means that the height, speed, doesn't depend on mass. But it only doesn't depend on mass if there's just Ke and Peg only. Doesn't work with springs. So mass cancels, but I can totally solve this problem. I would be putting in 1/2 v squared plus gh equals 9.8 h and solve for h. So if you wanted to, you don't have to calculate the total mechanical energy. You can just start from that equation that you wrote, cancel out the masses, and solve for the missing number. You can totally also do that. That will work until we get to next week. So let us sum this up so you can go try this on your own. Okay, so in summary, conservation of energy problems. Once you identify the system, calculate the total mechanical energy. Set the energy before equal to the energy after, so the total energy at A equals B, and use that to find either a missing height or speed. This is I know it's going to sound silly. This is going to be an easier to use thing than most other problem solving methods. And the reason conservation of energy is like beloved by physics students is that there are no vectors. So you're not going to have to do things like sine, cosine, tangent. The direction isn't going to matter. There's no kinematics equations involved here. For the examples you and I are working on right now, it actually even cancels out the mass. Right? A good thing about conservation of energy problems is they're what's called path independent. So check this out. Let's say I have a ball that's dropped straight down. Right? Its velocity just before it hits the ground, v down here, would actually be the same no matter what path it took. So even if it did this, the velocity at the bottom would be the same. Path independence means I don't even have to worry what crazy path it took to get from top to bottom. It could even do something like go way up into the air and then way back down and have the same final velocity, which is nice because path independence means I don't have to worry about any sort of like crazy directional things. As long as they are at the same height, they're going to have the same speed. Makes math way, way easier. Drawbacks that you should probably know about. You can only use it to find speed and height. I don't know if you noticed that. You can't use it to find mass or height or time. Sorry, not height. Mass or time or force. Since mass cancels out, you actually can't use that method very easily to find mass. And since it's not a vector, since everything in the problems are scalars, you can't use it to find any vector quantity. So you can't use it to find angle, direction, force, momentum, acceleration. impulse, anything that's a vector, you won't be able to solve for using this. So, like, the good thing is you don't have to use vector math. Bad thing is you can't use it to find any vector quantities. So what I want us to do is I want us to try this on our own. At this point, you've already done 1 through 5 on the homework. You did that on Tuesday. Yesterday, you did 6 through 8. I'm going to give us like half an hour to work here. For the next half hour or so, try these problems with the people in your breakout room. That way,